So since these are in series, we do add them up. The little hamster is gone for the weekend. Sorry. So the total resistance, 14 ohms plus 24 ohms plus 10 ohms gives us what? 48 ohms. Perfect. Then for part B, it wants the total current. Total current is just total voltage divided by total resistance. Gives us 0.5 amps, or if you wanted to, 500 milliamps, either way. For C, total power. Power total is just voltage total times current. So that's 12 watts. So those are the basics, getting the totals. Anybody have questions on those first three pieces? Okay. So the next, part D, asks for the power dissipated across resistor 1. Well, we know that the total current is 0.5 amps. Resistor 1 is 14 ohms. From the resistance, we can find the power. From the resistance and the current, I should say, we can find the power. Because power equals voltage times current, but voltage equals current times resistance. So I can replace that. The power is current squared times resistance. So the power dissipated in resistor 1 is 0.5 amps squared times a resistance of 14, which is, what is that, 3.5 watts, I believe? So E, the power dissipated in resistor 3, is the same formula. We just put in resistor 3 of 10. So it's the current of 0.5 squared times 10 is 2.5 watts. And now I didn't ask for the power dissipated in resistor 2, but if I did ask for the power in resistor 2, again, it's 0.5 squared times 24, giving us 6 watts. And those three numbers should add up to 12 watts, which is our total wattage created. F asks us for the voltage across resistor 1. Well, voltage is just current times resistance. Our 0.5 amps times our 14 ohms gives us 7 volts across resistor 1. G is asking for the voltage across resistor 2, V2. 0.5 amps times 24 ohms is 12 volts. And H, voltage across resistor 3, again, 0.5 amps times 10 ohms is 5 volts. And once again, you'll notice those add up to 24 volts, which is our total voltage for the circuit. So both voltage and power, voltage produced has to equal voltage dissipated, power produced has to equal power dissipated. Any questions on those? So number 2 is the same circuit with different numbers, so I'm just going to run down through the answers for you quick. So for number 2, A, total resistance is 240 ohms. B, total current is 0.1 amp or 100 milliamps. C, total power, 2.4 watts. D, power across resistor 1 is 0.75 watts. Power across resistor 2 is 1 watt. F, power across resistor 3 is 0.65 watts. G, voltage across resistor 1 is 7.5 volts. H, voltage across resistor 2 is 10 volts. And I, voltage across resistor 3 is 6.5 volts. Any questions on any of those? It's one of those ones, if you get the total current wrong at the beginning, everything else is done. Everything else is screwed up from there. Oh. This is only 240 or 24 volts here.
It says the E is equal to 120 volts AC.
Well, then I've got mine.
Yeah, that's why I completely had it wrong.
Let me take a look at your sheet.
Right there, you remember too? Yeah, that's why I just erased it because
Oh, yeah, I saw mine. I got the wrong number on mine.
Yeah, because
your numbers might be.
Well, I just erased them because I was confused. I was just like, wow.
Yep, so then on mine I have it written down as 24 volts DC. So let's go through it quick. You were probably right. Because I'm putting in at 24 volts DC, I'm only getting 0.1 amp. But yeah, if it's 120 volts AC, of course the AC doesn't change anything, but yes, it would be still 240 ohms, 0.5 amps, 60 watts.
That's what happened. 60. I was like, it's got to be 60.
Your power then across resistor 1 is going to be, what, 37.5 watts? Resistor 2 is going to be, no, that's going to be wrong. What am I? It's going to be 18.75 watts. Resistor 2 would be 25 watts. And resistor 3 would be, what, 16.25 watts? Voltage 1 is going to be 37.5 volts. Voltage 2 would be 50 volts. And voltage 3 would be 32.5 volts. Sorry. So now the voltages should add up. You're right. Good catch. So for number 3, let's make sure I've got the same numbers you do. Voltage is 24, R1 is 50, and R2 is 200? Okay, perfect. So 24 volts here, 50 ohms and 200 ohms. The start I've had to the day, I should probably just go home, huh? So anyway, total resistance. Here's where we have to do the reciprocals. 1 over RT equals 1 over R1 plus 1 over R2. We could have done R1 plus R2 over R1 times R2, but I like using that reciprocal. Turn on, darn it. There we go. So what we do is we put in the first resistance, 50, hit the reciprocal key, plus the second resistance, 200, hit the reciprocal key, hit equals, and hit the reciprocal again and hit equals. We got 40 ohms total resistance. For B then, if we have 40 ohms total resistance, our total current then will be our 24 volts divided by 40 ohms is 0.6 amps or 600 milliamps if you prefer. 6 then I1. Well, remember in a parallel circuit, the voltage is the same on both branches. So it's just the 24 volts divided by 50 ohms, giving us what, 0.48 amps. And then for DI2, 24 volts over 200, 24, not 42, 24 volts over 200 ohms gives us 0.12. Come on. I have those wrong on my answer key too for some reason. Oh, they're there. Looking at the wrong problem. Then my voltage is, well, voltage across resistor 1 is going to be 24 volts. Voltage is the same no matter where. Power, total power here, power total, is total voltage 24 volts times total current of 0.6, 14.4. And finally, power across resistor 1. Well, that's going to be the current across resistor 1 is 0.48 times the voltage across resistor 1 is 24. What's that give us? 11.52? Okay. For number 4, again, a similar thing, only there's 3 resistors in series. So to find my total resistance, it'll be 1 over 90 plus 1 over 450 plus 1 over 150. So 90 reciprocal plus 450 reciprocal plus 150 reciprocal equals, we have 50 ohms is our total resistance. So then for total current, voltage divided by resistance, yes, 24 divided by 50 is 0.48 amps, or 480 milliamps. I1, well, that's going to be the 24 volts across 90 ohms. Is that like 0.2667? I2 is still the 24 volts across 450 ohms, 0.0533. And then I3, the current through the third resistor, is just still the 24 volts over the 150 ohms, which is what, 0.16 amps. F, total power, is going to be the voltage of 24 times the total current of 0.48, 11.52. And G, power through 1. Well, we found I1 is 0.2667 times the voltage of 24 is 6.4. H, power 2. We got the current through 2 of 0.0533 times voltage of 24 gives us 1.28. I, power through resistor 3. What is that? 0.16 is that current through 24 volts. 3.84. Now again, hopefully if I add these up, I get my total of my 11.52. I think they do. And then, of course, finally for J, find V1. Well, the voltage across any of those resistors is going to be 24. Full voltage across parallel resistors. So this one, number 5, yeah, I'm going to end up redrawing it probably just to make it fit the way my brain grasps these things. So this is the way you would probably see it set up in a standard circuit diagram. My brain grasps it much better, as I mentioned last time, if I put all the resistances down the right side. So I would redraw it like this. This is 120 volts. As I go around the circuit here, I hit the 30 ohm resistor, so I go overcoming down. I'll put my 30 ohm resistor here. Then I hit a branch where it branches off. So I'm going to split this. One side of the branch I have 75 ohms. On the other side of the branch I have the 100 and the 200 ohms. They come back together and then go back to the voltage source. So for me, redrawing it like this just makes it easier to analyze. So to find the total resistance, we can't just plug into a formula. We've got to go piece by piece. So the first piece we have is this part. They're in series, so what do? Add them together to get 300 ohms. Now then we can replace this whole section. We get a piece here that is the combination of the 75 and 300. So we have to use that reciprocal key again. 75 reciprocal plus 300 reciprocal equals reciprocal 60 ohms. So this whole branch here was just reduced to 60 ohms. Then that is now in series with the 30 ohms here, so we add them together to get 90 ohms total resistance. How many of you had 90 ohms? 79? Oh, sure. It's one that makes so much more sense if you can draw it with all the resistors on top of each other like that. So for part B, total current. 120 divided by 90 gives us, 1.3333. C. I was going to say, I asked for total current again. Apparently, I really wanted to make sure you knew how to do the total current. For D, I1. So current 1 is just the total current. Whatever the total current is here has to go through I1. There's no place for it to split. I2, however, now the current splits up. Part of it's going this way, part of it's going this way. So to figure out how much, we have to go back to finding the voltage drop across this first resistor. That voltage drop there, V1, which is going to be calculated later, I believe. Yeah, it's part M. That voltage drop is just our total current, the 1.3333 amps, times the 30 ohms, which is going to give us 40 volts. So if there's 40 volt drop there, how much voltage is left over the rest of this circuit? 120 minus 40 gives us 80 volts. Now that we know there's 80 volts across this branch, R2 is just this resistor here. The full 80 volts goes across that. So it is 80 volts over 75 ohms, or 1.067, I believe, amps. F, the current through I3. Well, again, we're looking at this other half of the circuit over here. This side is 300 total ohms. So we have 80 volts over 300 ohms, which gives us 0.267, I believe, amps. And then G is asking for I4, which has to be the same. Whatever current goes through here has to go through this one as well, because they're in series. For H, total power, we have 120 volts times our total current of 1.333 equals 160 watts, I believe. I, power through resistor 1. Well, we have the current of 1.333 and the voltage of 40, 53.333 watts. J, power 2. So power 2, we had a current there. Where's current 2 go? 1.067 times the voltage of 80 volts. Multiplies to 85.333. Power through 3, we have a current through 3 of 0.267 times a voltage of, well, 80 goes through the whole side over here. So we have to break this down and get a voltage for each one separately. So the 0.267 times 100 is 26.7 here, volts. And then times 200 is going to be 53.3 volts there. So this is going to be through times 26.7. Sounds right. Yep. So 7.13 we'll call it. Watt. Then for L, power through 4, well, that's the 2.67 amps, but that was 53.3 volts. So it ends up being, what, 14.26, something like that, watts. Now, all this is rounded because these came out to be 0.333, 0.667. So if you were to add up those wattages, you might be off by a couple of thousandths, just getting your total right, but it's going to be really close. It's all just a round off. Let's see. Where am I at? I'm at M. Voltage across 1, we've already found that to be 40 volts. N, voltage across 2, we already found that to be 80 volts. Voltage across 3, we just found to be the 26.7. And voltage across 4, we found to be the 53.33. Any questions on that one? Okay, flipping over to the back side. So number 6, we have A is, I'll draw my basic little picture here. So A is this distance. B is the distance to the flange. So if A is 16 and B is 10, how much should the near foot, so this is point N, the near foot here. So how much should the near foot be shimmed to raise the end of the shaft 0.026 inches? So it's the 0.026 over the total distance is what we want here. When we're shimming the near foot, this becomes our pivot. So the distance from the pivot is just the point that stays in the same spot. So the distance we have to get is from that out to here. So that's going to be the 10 plus 16. Then that's going to be compared just to the distance between the feet, because that's how much. That's where we're going to put the shim of 16 inches. So we add those to get 26, and we cross multiply and divide. So 0.026 times 16 divided by 26, we get 0.016 inches is our shim. Did you plug it in wrong somehow? What'd you have?
0.0165, but I didn't add 10 and 16 together.
Okay. Sure. So number 7, vertical angular gap if V0 or V12 is 0.112 inches and V6 is 0.098 inches. All we have to do is subtract them. 0.014 inches is our vertical angular gap. Number 8. So same picture, only now A is 12 and B is 8. This time we're going to be shimming the foot M. So we're going to be shimming here. So N is going to be our pivot. Now, we want to know how much would the end of the shaft drop if we had 0.027 inch shims. So the shims are going to go here at point M. The distance to the pivot is just going to be the distance A, which is 12 inches. So that 0.027 is over 12. Then from that pivot, get back here. From that pivot to the end of the shaft is this distance here. That was just B, which is 8. So over 8. And again, cross multiply and divide. So 0.027 times 8 divided by 12. So we get 0.018 inches. We have to shim that. Some textbooks define something called a shim ratio. Rather than setting up a proportion like this, they say take the 0.027 and multiply by a shim ratio of 8 to 12. Well, it's the same thing. I like setting up the proportion because once you find the pivot, the fixed point, then it's just measuring your distances from that fixed point to set up your proportion. So number 9, if the shaft is operated at 2,700 RPM, what is the allowable angular gap? This is in your books on that table. Oh, what is it? Page 326, yes. I guess I listed it on there for you. So if we're looking at 2,700 RPM, what is our allowable angular gap on a 10-inch flange? 0.005. So page 226, there's a table that has speed and then excellent and acceptable. So we're using the acceptable, 226. 326, sorry, 326. So the acceptable is for a 10-inch flange. If we are using, as it says here, a 4-inch flange, we have to reduce that angular gap. Exactly. So I should get 0.002 inches. Is that allowable angular gap? Everybody see where we got the 0.005 out of the table? Any questions on that? Then that is the rating for 10 inches, so we put it over 10. We need to find the rating for 4. So. Problem number 10. Shaft is operating at 1,400 RPMs. We need to find what's the allowable angular gap for a 6-inch flange. So at 1,400, what would be acceptable? 0.010. That's on a 10-inch. We want to know for a 6-inch. If you cross multiply and divide, 0.006, 6,000ths of an inch. Perfect. Number 11, the angular gap is 0.084 inches. We want to find the size of the shim required if the mounting holes are 16 inches apart. Do you guys know what that abbreviation MTBS means? Machine to be shimmed. MTBM means machine to be moved. So our distance between feet is 16 inches. And we have an angular gap of 0.84 that we want to close up. So we take our 0.84, or 0.084, I should say. And we need to know what is its moment arm. Well, we have here, what's the size of that flange? 4-inch flange. 4 inches, however, is not our moment arm. Our moment arm is from the center of shaft to the edge of the flange, which is 2 inches. It's half of the diameter. The radius of the flange is what we want. So that 0.084 inches is acting on a moment arm or a radius of 2 inches. So 2 inches goes under that. We need to know then how far do we have to shim it on a 16-inch. We're going to be shimming here probably and pivoting there. So then again, it's cross multiplying. What numbers get multiplied? You got it. 0.084 times 16 and divided by the 2. 0.672 is correct. That's a lot of shimming. I was say pushing 3/8 of an inch, yeah. Or 5/8 of an inch. Over 5/8 of an inch. Number 12, if the gap at 6 is 0.279 and the gap at 12 is 0.301, so the first thing we're going to do is we're going to subtract those to get the vertical angular gap, which is what, 0.22? If we subtract those, so that is our vertical angular gap. Find the size of the shim required. This is an 8-inch flange, so we put our vertical angular gap of 0.022 over 8-inch flange. The mounting holes are 11 inches apart. So we'll cross multiply and divide. 0.022 times 11 divided by 8. 0.03025. So basically you're going 30 thousandths is what you're probably going to shim. $13. So how many threads are required to go 1/4 inch on a 24 TPI? So we want to go 1/4 inch, or not 1/4 inch, 0.125 inches. Each thread one thread is equal to 1/24 of an inch. So it's the 0.125 times 1 divided by 1/24. So to do this, you have to be careful. So 0.125 times 1, of course, is just going to be 0.125. When we divide by the 1/24, I use parentheses, divided by parentheses 1, divided by 24th, and close those parentheses. I get 3. So 3 turns. Three turns should bring you up to 0.125 inches. 14. What's that? If you just do the point, oh, that does work in this one, but that won't work always. Got 8. Sure. Multiplied it out. So how far does a plate move on a 20 thread per inch bolt if it's turned 2.75 turns? So 2.75 turns, if one turn is 1/20th of an inch. So we got 2.75 times the 1 divided by 20. So times, I put that in parentheses again, 1 divided by 20, close that up. Then divided by 1 isn't going to change anything, so it's 0.1375 inches. Okay. As long as the method you've got is they're giving you the right answers, stick with her. There are about 4 or 5 different formulas I know of that'll work with this. "15, find the change in length if an 18-inch piece of steel, which has a thermal factor, thermal coefficient of 0.009 inches per degree Fahrenheit, is heated from 70 to 132. So first thing we have to do is subtract. How much did our temperature change? So 62 degrees Fahrenheit is our temperature change. So then our elongation, if you remember, elongation is the original length times the change in temperature, that's the 62 degrees, times the thermal factor, which gives us like 0.01044 inches, something like that. So basically 10 thousandths of an inch is what it's going to change. On an 18-inch piece, you usually don't have to worry a whole lot about thermal factors. It's when you got a few feet that you start worrying about thermal expansion. So again, find the change in length if you have a 9-inch piece. So we have 9 inches. The thermal factor of 0.000123 for aluminum. And the temperature goes from 68 to 148. So again, 148 minus 68 is 80 degrees. So 80 degrees goes in the formula here. So 9 times 80 times that thermal factor. 008856, you got it. So about 9 thousandths of an inch would be your expansion there. Okay, for 17, these are just simple voltage and currents. So find the voltage for these for number 7 or 17. You're just going to take the current times resistance to get 56 volts. For 18, current times resistance again, but the difference is the current is 45 milliamps. You got to change that to 0.045. The resistance is 2.4 kilo ohms. That's 2,400 ohms. 108 volts. You got it. If you get more into electricity, you start to learn that a milli and a kilo cancel each other out when you multiply them together. So you actually could have just multiplied the 45 and the 2.4, and it would give you the right answer. But you have to make sure you're very careful with your units. If you have a mega ohm resistor, that doesn't work. You've got to have a kilo and a milli times each other to cancel out. So for power of 3.6, we're going to divide by the current of 0.03 amps to get 120 volts for number 19. Number 20, we got a power of 48, current of 20 milliamps. We got to change that to 0.02. 48 divided by 0.02 gives us 2,400 volts. 21. So this one's a little trickier. We've got the power of 480 milliwatts. I'm going to write that in as 0.480. We've got a resistance of 1.2 kilo ohms. I'm going to write that as 1,200 ohms. The formula here is power equals voltage squared over resistance. So to solve for voltage, I have to multiply by the resistance. So power times resistance equals voltage squared. And then we have to take the square root. So we end up getting that the voltage equals the square root of power times resistance. So we punch that in, the square root of 0.48 times 1,200. Make sure we close our parentheses on the square root. We get 24 volts. Yep. (22) is going to be the same thing. This is going to be the square root of 16 watts times 3,600 ohms. Gives us 240 volts. For 23, we're finding the current. Voltage of 120 volts divided by 600 ohms is 0.2 amps. 24, we have 24 volts divided by 1,200 ohms. It's 0.020 amps or 20 milliamps. 25, calculating the current from the power and resistance now. Power equals current squared times resistance. So to solve that for the current, we divide by the resistance and then take the square root. So the current is the square root of the power divided by the resistance. So for 25, it's the square root of 4.8 watts divided by 3,000 ohms. So second square root, 4.8 divided by 3,000 gives us 0.04 amps, or 40 milliamps if you would prefer. 26, same formula, square root of, so it's milliwatts, that's 0.06 watts, divided by 1.5 kilo ohms is 1,500 ohms, give us 0.0063 amps, or again, 6.3 milliamps if you prefer that notation. So 27, Find the resistance. Voltage of 24 volts divided by current of 0.048, because the 48 milliamps gives us 500 ohms. For 28, for power, remember power, we're given the voltage here, so power is V squared divided by R. If I solve that for R, I get the resistance is V squared divided by P. So it is the voltage of squared, 120 volts squared, divided by 4.8 kilo is 4,800. Ends up giving us 3 ohms. How are we doing? Are we ready for quiz? I'm sensing a little tentativeness there, but let's go for it. You can take a break whenever you need to if you need to go do something. Is it? There we go. Thank you. So anyway, thanks for reminding me. So the inductance in the coil is measured in a unit called henries. A henry is a very, very large unit. So quite often when we're dealing with inductors, we're dealing with maybe millihenries, most often microhenries for the size of that inductor. And all that does is it basically is saying what size of a magnetic field it can produce compared to its current. So the inductive reactance, which is the amount of resistance that that component will give to flow of current in a circuit, is that formula there. XL is the inductive reactance. 2 is just a constant. Pi, you probably know is that constant, 3.1415926, blah, blah, blah. There's a pi key on your calculator, or you can just use 3.14. F is the frequency. Does anybody know standard frequency of a circuit? 60 hertz. 60 hertz American. If you're in Europe, it's 50 hertz. And this is something to be careful of. I've seen European machinery shipped over. Got to be aware of the possible difference in frequency. L then is the inductance in henries. So if we have, well, let's do 60 hertz and 50 millihenry circuit. Find the inductance, or the inductive reactance, I should say. XL equals 2 times 3.14 times 60 times millihenries. So this is going to be 0.050. Remember, when you see milli, that means you have to divide by 1,000 to make it into regular units. So if we multiply that out, 2 times 3.14 times 60 times 0.05. Oops, I didn't like something I put in there. Let's try that again. 2 times 3.14 times 60 times 0.05. There we go. 18.4. 0.84, I should say. And that is going to be measured in ohms, just like a resistance. So if we still have a 60 hertz circuit, and this time we have an inductance of 200 microhenries. We haven't used the unit micro yet. Micro, to get from micro to the regular units, is dividing by 1,000,000. So this is going to be 2 times 3.14 for pi times 60 times 0.0002 is what that 200 microhenries. If we do 200 divided by 1,000,000. My calculator's come with scientific notation. 2e negative 4 means you move the decimal point 4 spots to the left, so it's 0.0002. Has anybody else had that pop up on their calculator? We get that E with a number after it. Okay. What that is scientific notation. So I have the 2e negative 4 there. The negative on the 4 means you have to go to the left. And the 4 means you're going 4 decimal places. So the decimal point is right there. 1, 2, 3, 4. Fill in the zeros. That's 0.0002. If it's a positive number, you go to the right with the decimal point, however many places. Okay, so if we multiply this out, 2 times 3.14 times 60 times 0.000, oops, well, that did not work. 2 times 3.14 times 60 times 0.0002, 0.07536. You see we're getting relatively small numbers for the ohms. And that is because these don't have a whole lot of pushback on the circuit unless you have some sort of outside magnetic force on it, draining it. Okay, well then back up to capacitive reactance. So a capacitor is 2 parallel plates. Now they could be just 2 solid plates parallel, or they could be flexible foil plates that are wrapped with some sort of an insulating layer between them. All it is you build up charges. So if you hook it to a power source, you'll build up positive charge on one plate, negative charge on the other. Or in other words, you build up a bunch of electrons on the negative plate and you have a negative net charge. You unhook it from the power source, this will store that charge. You can hook it back up and it'll release it. So you can actually use it to power a circuit for a very short period of time. Capacitors are usually used to protect against power surges and any little bumps in the power. They're to even out the current in general. So they obviously can have a huge reactance, a huge stoppage in the flow. If this is a DC current, a DC circuit, a capacitor, once it's charged, has an infinite resistance. No current can flow through it at all. So we're only dealing with AC circuit here. The capacitive reactance is 1 over 2 times pi times the frequency times the capacitance. So if we have a frequency of 60 hertz and a capacitance, our capacitance is measured in farads, by the way. If we measure, let's see, we have 40 microfarads. Now farads, again, are a very large unit similar to henries. Typically, when we're dealing with farads, we're dealing with micro or picofarads, very small. So micro, of course, is divided by 1,000,000 still. So it's 0.00004 farads. So our formula there would be our capacitive reactance is 1 divided. Let me write it out the way we'd punch it in the calculator here. So 1 divided by parentheses 2 times 3.14 times the 60 hertz times 0.00004. Then make sure you close your parentheses. Okay, 66.35. And again, that'll be measured in ohms. I'll let you guys try one. I get a frequency here of 60 hertz still, a capacitance of 500 picofarads. Pico means divided by a billion. I said a farad is a huge unit. We got to use very tiny prefixes to make it small enough to be useful. So with the picofarads, the 500 picofarads becomes 0.0000005 farads. So 6 zeros in front of that. We plug that in, 1 divided by parentheses 2 times pi times 60 times our 0.0000005. Close the parentheses, we get 5,307.86. So capacitors create a very large resistance in a circuit. These can be used for like test circuits and stuff like that. It has a large resistance, so it doesn't drain a lot of current out of the circuit. Or test branches, I should say, not test circuits. So next thing we want to discuss is something called a power factor. Power factor is simply going to be a percentage. And it's a percentage of utilized power. If you ever look at a tag for a motor, there's a lot of information listed there. Usually there's the voltage, there's the current. If you have a low-high motor, there'll be 2 currents listed there. And there's going to be a horsepower rating. If you look really closely, you usually find that those numbers do not necessarily match up. So first of all, you need to know that 1 horsepower is 745.7 watts. A lot of times we just use 746. Let's say that we have a motor that is rated at 240 volts and 1.4 amps. This is an apparent power of just that rated voltage times the rated current. Bless you. So if we multiply that out, 240 times 1.4, we get 336 watts. So that is the apparent power. If we're looking at that motor, that's what it looks like that motor should draw. However, the rating of the motor usually doesn't match up. So let's say we've got this. Let's look at another motor here that is rated 1/2 horsepower, and the tag says it is 2.6 amps at 240 volts. Well, first thing we need to do is find the actual horsepower, or the actual power, I should say. And that's just by converting the horsepower into watts. 1/2 horsepower times 745.7 gives us 372.85 watts. So that's the actual horsepower that that motor is capable of putting out, according to its rating. The apparent horsepower, or the apparent power, not horsepower, is again the voltage times the current for the rating. So 240 times 2.6 gives us 624 watts. Now I should be careful. Technically, they usually don't rate this in watts. They rate it in volt amps. A voltage times an amp is a watt, but in certain situations, like in transformers and things like that, they keep it as volt amps because it's not truly a watt. It's not truly dissipating that power or using that power. It's just a rating. So then our power factor is the rated power over the apparent power. So here we have the rated power, the 1/2 horsepower of 372.85 over the apparent power of 624. So we take 372.85 divided by 624, and we get 0.5975. We should go 4 digits at least on that, and then convert it into a percent. Well, to make it a percent, just move that decimal over 2 spots. So what this is saying is the actual power of this motor is only 59.75% of the apparent power draw if you go at max voltage and max current. In your notes, I want you to try to find for you the power factor for a 1/4 horsepower motor that is rated at 1.9 amps at 480 volts. I'll give you a minute, then we'll go through that. So we have the rated horsepower of 1/4 horsepower times 745.7 gives us 186.425 watts if it's running at full horsepower. The label, the tag, gives us 480 volts at 1.9 amps, which is 912 volt amps. So we divide the horsepower, the 186.425, divided by the apparent, the 912. That should give us 0.2044 or 20.44%. Questions? Okay. What have you guys talked about with transformers yet? Anything? No? Okay. So transformers are basically a pair of inductors. They work off of mutual inductance. And we'll get to the actual transformer ratios more in 2 weeks when we meet again. For right now, I want to talk about configuration. There's two types of configuration. There's a Y configuration and there's a delta configuration for transformers. So a Y transformer is 3 inductors that are connected in the center. Pretend those look like coils. And they are actually oriented in a circle like this, evenly spaced, which means that the angle between any of them is 120 degrees. Most Y-configured transformers are center grounded. So that symbol's the ground if you're not familiar with it. And so in a center grounded Y, the geometry actually works out for the voltages and the currents. Let's say that each phase, each of the inductors is referred to as a phase. Let's say that each phase has 120 volts on it. When we hook up using a Y-configured transformer, often what we're doing is we're hooking between two phases. Rather than from a standard single phase, you're hooking one phase to ground. In 3-phase, you're hooking up between two of the phases. So if I am connecting between, and just because I drew the ground there, we'll connect between those two. The voltage between those two phases is not a full 240 volts, because for that to be a full 240 volts, the phases would have to be opposing each other like this. And they're not. They're at an angle. This is 120 degrees between here. That makes this 60 degrees. And so this distance here, that shape there forms a right triangle. If this is 120 volts here and this is 60 degrees, and this is my right angle, this opposite side is the opposite side. Opposite side and hypotenuse form the sine. If you recall a little bit from 2 semesters ago, the sine of an angle is the opposite side over the hypotenuse. So to find this size over here, that amount, we have the sine of 60 degrees. I'm going to put it over 1. The opposite side is what I'm looking for, and the hypotenuse is 120 volts. So I do sine of 60. Now here's something you should check on your calculators. Punch in sine of 60. Make sure it gives you 0.866. If it does not, your calculator is probably set in radians rather than degrees. 0.866 is what you got. Okay, then times 120 and divided by 1, we get 103.9. Basically 104 is what we get. Did you get something different than the 0.866? Yeah? Oh, so your cell phone, some of your cell phones are automatically set for radians, and I'm not totally sure how this. So this is the setting here. You got to change there. You just have that degrees. What's it? There it is. Yep, just this side. And type in 60 and then 2. You don't have to. Oh, so you got to get into. Yep. Get a little bit of the classic. Now when you take it from 2 degrees, just sort of so this is where when they talk about industrial voltages, you hear a lot about 120, 240, and 480. But the actual industrial voltage that comes out of here, if this is 104 and this is 104 over here, is 208. So a lot of machines are running, they're rated at 240 volts, but they're running on 208 because that's what you pull off your transformer. And it's just because they're not fully opposing because of the angle between them. Yep. So the key number there is actually that sine of 60. A couple of you had your calculators in math type mode, it gave you the square root of 3 over 2. Well, if you double that because you've got two wings, it's just the square root of 3. So the square root of 3 is actually your conversion factor. If you have a line voltage of 120 volts, your phase voltage, I should say, of 120 volts. So it's 120 volts in each phase. If you connect between those phases, your line voltage will be 120 volts times the square root of 3, which gives you the 208. So if I know that let's do some notation here to speed it up. So that is the phase current. So that's the current in the transformer. That's the phase voltage. The line current then is I with a little L. The line voltage is V with a little L. Conversion between them, if you know the phase current, you multiply by the square root of 3 to get the line current. Makes sense. The voltage increases by the square root of 3, the current's going to increase because the resistance will stay the same. If you want to find the phase current, and you know the line current, you divide by the square root of 3. So let's say we have a 20 amp phase current. The line current is going to be 20 times the square root of 3. And you can just type in 20 times the square root of 3, gives you 34.64 amps is your line current. So because of this, to figure out your power, the power is the square root of 3 times your line voltage times your line current. So if we have 120 volts drawing 15 amps, our power is the square root of 3 times the 120 times the 15. So if you're going to put in the square root of 3 first, you do have to make sure you close the parentheses before you do times 120 and times 15. So 3117.69 watts. Any questions? Okay, we are out of time. It's lunchtime. I did pass out the worksheet while you're working on the quiz. We'll go over that just like we did this time. We'll go over the worksheet first when we get back next time. Answer any questions on the quiz before you hand it in. And then we'll go from there. We may scrap the second quiz and just do new material next time and not make you do another quiz.